Welcome to module 34 of database management systems. In this module and the next, we will talk about concurrency control, a very key concept of database transactions. So, in the last module, we have talked about continuing on the transactions, we had talked about recoverability of databases, how to satisfy the ACID properties, the basic transaction in SQL, and we have introduced a second form of serializability in terms of the view serializability. Now, here in this we will talk more on the different aspects of concurrency control, because it is good that if two schedules are given, we may try to prove if they are conflict serializable, if they are view serializable, and then we can use them. But doing that in general while the database is in execution is an extremely difficult problem, because who is going to give the who will be able to give the all possible different types of transactions that may happen, hundreds of them that may be going on in the database at any given point of time. So, how do you prove that or how do you know whether they are conflict serial, or which of them are conflict serializable sets or view serializable sets and so on. So, we introduce a different kind of need to have a different kind of mechanism, and that is the mechanism of lock that is used. So, we will discuss about those aspects, issues, and the lock based mechanisms. So, a database must provide a mechanism that will ensure all possible schedules are both conflict serializable, that is a basic requirement, and are recoverable, and preferably in a cascade-less manner. So, that is the basic requirements that we have seen. Naturally, if we have everything as serial, that will happen by default, but that will have very poor degree of concurrency and very low throughput. So, concurrency control schemes will trade off the amount of concurrency that is allowed and the amount of overhead. So, what will have to be ensured is I should be able to, for example, if I say that the schedules are always serial, then the overhead of ensuring concurrency is the minimum, but naturally the benefit is also minimum. We get a very poor throughput. The more we would like to allow for more and more concurrency in the system, but at the same time we will need to have to see what is the overhead of that, what is the cost of that, how do we have to ensure those. And naturally, as I have already said, testing for a schedule to be serializable after it has happened is obviously too late, and the question is beforehand, how do I get to know it in a general setting. So, we need to have a certain protocol through which the transactions must be written, a protocol through which the transactions must operate, so that we can achieve good concurrency in the system. So, here our objective is to develop concurrency control protocols that will ensure serializability and if possible cascade-less recovery. So, naturally, what you do, you try to see whenever we have conflict, our basic problem of serializability is conflict, that is what are you reading the right data, and what happens if you inadvertently make changes in a data that has already been read by someone else and so on. So, the way to achieve isolation of the transactions would be to make the accesses as mutually exclusive as possible. So, naturally one way could be to do it using lock. So, the basic concept of the lock is you say that this data item is in use, so others should not use it. Now, what should be the data item? Should it be the whole database? It can be the whole database. We say this database is in use, other transaction cannot use it, which boils down to saying almost that you have a serial schedule. So, at any point of time only one transaction can operate on the database, naturally your concurrency will be very poor. So, that is not what is acceptable. So, we need locking mechanisms or a mechanism to control exclusivity in terms of holding locks on smaller items, possibly at a record level, at a value level, and so on. So, that gives rise to a whole lot of lock based protocols, some of which we are going to discuss. So, lock is a mechanism to control concurrent access, and to start with, there are a variety of locks that exist in a database system, variety of types, but to start with we are talking about two locking modes. One is exclusive mode, which is designated as X, another is shared mode, and which is designated as S. Naturally, in the exclusive mode, the data item can be read and written both, and such a lock is obtained by doing a lockx instruction, and in the shared mode the data item can only be read. So, as you can understand, why is it exclusive when you do read write? Because if two transactions try to write the same item at the same time, then you do not know who has been successful and who is the last write and what is the actual final value. They will become indeterminate. But if I have a value and multiple transactions read that at the same time, certainly there is no problem, because all of them necessarily will read the same data. So, that is what is called shared, and a shared lock or a shared mode lock can be obtained in terms of the lock S instruction. And a transaction, when it has a lock, it can unlock that by an unlock on the same data item. So, there is a concurrency control manager to whom the lock requests are made, whether it is a request to grant or it is a request to release, and a transaction can proceed only after the request has been granted. So, let us look into finer details. This is what is known as lock compatibility matrix. So, if there are multiple lock modes, which is what is expected, then you try to see which locks can be held or operated simultaneously. So, this is shown in terms of our present assumption, that is shared and exclusive lock. Naturally, two transactions can hold a shared lock simultaneously on the same data item, but all other combinations, that is no two transactions can hold a shared and an exclusive or two exclusive locks on the same data item at the same time. So, which means that two transactions can read a value at the same time, but two transactions cannot. One is reading the value and other is writing the value is not possible. The reverse is also not possible, and two transactions writing the value is not possible. Those are said to be the incompatible modes of locks. So, if the transaction is granted a lock, if it is compatible with the lock that is already held by another transaction, you cannot get an incompatible lock granted to you. And any number of transactions certainly can hold the shared lock on an item, but if any transaction wants to have an exclusive lock on the item, then no other transaction may hold any lock on that item. So, if I want to write that as a transaction, I must be the only transaction who has to have that exclusive lock. I must be the only transaction who is trying to write, but when I want to read, many transactions can simultaneously read. So, if a lock cannot be granted, that if I want a lock, either a shared lock or an exclusive lock, and if it cannot be granted, then the transaction has to wait till all incompatible locks have been released, and only then this lock can be requested lock can be granted. And certainly a transaction which is holding a lock on a data item can unlock it at some point after its purpose of accessing the data item is over, and a transaction must hold a lock on the data item as long as it is accessing the item. That is a basic protocol. So, you must request first, get a grant of that lock, do the operations that you want, and then you unlock. This is the basic process that has to happen. Usually it is said that as soon as you are done with the operations of the data item, you may not unlock that. You may want to wait for a little longer for the ensuring the serializability. These details we will see subsequently. So, let us come to an example. So, here are two transactions T1 and T2. So, this is the two transactions T1, T2. The transaction T1 does this operation, it transfers $50 from account B to account A. So, it debits B here, credits A here. So, it transfers, and transaction T2 displays the total sum of money in the accounts A and B. So, it reads A, reads B, displays. And say initially the transaction, let us say these accounts have values 100 and 200. So, what this transaction will do? It needs to do the transfer. So, it needs to read B, debit and write, and what it has to do, since it has to read, it must have a shared lock. Since it has to write, it must have a exclusive lock, and if it has got an exclusive lock, it will also be able to read that data. So, what it does, it performs an exclusive lock. So, it requests for an exclusive lock, and only on getting that it can do this, and when this is over, the purpose is over, it unlocks B. Similarly, to update A, it takes an exclusive lock on A, updates and then releases the lock. Transaction T2, what it does, it has to read and display. So, it does not need an exclusive lock, it takes a shared lock, reads and unlocks. It again takes a shared lock on B, reads and unlocks, and finally displays the two data. Now, if these transactions are executed serially, that is T1 after T2 or T2 after T1, then the transaction T2 will always display the value 300, because 300 is the initial value that we will be able to see if T2 runs first, and T1 300 is also the final value, because only $50 has been transferred from B to A. So, the sum remains same. So, you will be able to see that if T2 runs after T1. So, the consistency of the database is maintained. Now, let us see. Let us consider a schedule written here as schedule 1, and the transactions are executing concurrently. So, then this is a possible schedule, and let us see what will happen. So, what it does, this is where the lock, exclusive lock on B is held and B is updated, then A is read, then B is read, display is done, and then this update on A has happened, and this is where we are showing that how the grants are happening. So, as the lock is requested, then the request goes to the system that a exclusive lock on B is requested by transaction T1. So, that subsequently gets granted, and only when the grant has happened, the corresponding access can start. But it can be any indeterminate amount of time between the request of the lock, which is here, and the actual grant of the lock. But this operation can happen only after the grant has happened. So, in every case, that is what has to be observed. Right? Now, what happens in this schedule? What will be the consequence? So, in this schedule, if we look at the transaction T2 will display only $250, it will not display $300. Why? Because if you look at this carefully, this is where B has got updated. So, B has become $50 less, and then the whole of A and B have been read and displayed. So, naturally the total sum is $50 less. So, even though we have used a lock, it has not been able to achieve the required even though we have used the lock, we have not been able to achieve the required serializability, and it is possible to create a schedule where inconsistent data is getting generated. T2 is actually reading an inconsistent data. So, you have seen an inconsistent state in terms of here. Why did it happen? This happened because if you look carefully, this has happened because T1 has unlocked too prematurely. T1 has unlocked as soon as the update to B was over. So, it was possible for T2 to read that value of B, which is not what is desirable, and we will see that we might want to delay the unlocking till the end. Let us see what happens if we do that. So, we are here now, it is the same transaction in terms of the notion, but T1 has been made to T3 here, where you have seen that unlocking is been pushed to the end. T2 has been made into T4, where the unlocking is pushed to the end, and now naturally if you look into this, if you wanted to do a schedule 1, you cannot do this kind of a schedule 1, that schedule will not be permissible, because you will not be able to get the locks, T4 will not be able to get the locks that T2 could get. Hence, the sequence of reads and writes in schedule 1 is no longer possible. So, whatever way we actually do the schedule, T4 will always correctly show that the sum is $300. So, here we are again showing T3, T4. This is a schedule given, schedule 2, which is just given partially, and since T3 is holding an exclusive lock on B and T4 is requesting a shared lock. So, if I hold it, this is T3 is holding an exclusive lock and T4 is requesting for a shared lock. So, T4 has to wait for T3 to unlock B before it can actually do that operation. Similarly, you will find if you look further, T4 has already got a shared lock to read A, and T3 needs a shared lock on, I am sorry, T3 needs an exclusive lock on A to be able to proceed. So, there is one is here. So, T4 cannot go beyond this point, because T3 has the lock on B, and one is this, T3 cannot go beyond this point, because T4 has that shared lock. So, what situation are we getting into? So, we are getting into a situation where neither of T3 or T4 can actually proceed the normal execution. T3 is waiting for exclusive lock on A, and which T4 has, and T4 is waiting for the shared lock on B, which T3 already holds as an exclusive manner. And this is what is called deadlock. If you have studied operating system, then you must be knowing deadlock very well, and the deadlock happens through different other issues of sharing resources. Here it is because of the lock. So, moment you use locks, there is a possible danger of having deadlocks, and once you have a deadlock, there is no other way than to unroll one or more of the transactions and start all over again. So, it has to roll back one of the two transactions to be able to proceed. And once the transactions are rolled back, the data items that were locked by the transactions will also be unlocked. So, please understand this in view of the earlier discussion we had in terms of TCL commands. So, when you actually issue a rollback, we had at that point could only say that your value of the data item in the database will be rolled back, but certainly as now you can understand that if you roll back, also the locks that you had acquired will also get unlocked, so that other transactions can get those locks and proceed. So, then the data items become available for other transactions, and that can continue the execution. So, if we do not, so we are saying that we wanted to use locks to get better control on the serializability and so on, and it was partly possible, but then we are getting into different other kinds of different problems. So, if you do not use locking, or if we unlock data items very early, then after reading or writing them, then we may get inconsistent state. This is what we have seen. On the other hand, if we do not unlock a data item before requesting a lock on another data item, that is, if we hold it on for a very long time, then deadlock may occur. So, if we do it too soon, we do not use the lock, that we have a problem of inconsistent state. If we do it, hold it for too long, then there could be problem of deadlock. Now, deadlocks are necessarily evil of locking. If you do locking, you will always face deadlock if we want to avoid inconsistent states. Now, between these two, obviously we would prefer deadlock, The reason we will prefer deadlock to inconsistent state is the fact that if we have deadlock, we still have the option of rolling back, and we can take different strategies to decide what to roll back and how much to roll back and so on. Whereas, inconsistent states may lead to real world problems that cannot be handled by the database system. In fact, in many cases I may get into some inconsistent state which is very difficult to even recognize that it is an inconsistent state. So, we will continue and prefer deadlocks over inconsistent states, and we will try to define different locking protocols, a set of rules that the transactions should follow while the request and release locks to make our life relatively easier. So, locking protocols necessarily will restrict the set of possible schedules, because we will put in some discipline in terms of how we lock and how we release them. And the set of all such schedules is a proper subset of possible serializable schedules, that is easy to understand. And we will present locking protocols that allow only conflict serializable schedule, which ensures isolation. So, let us look at the most widely used protocol. This is called the two-phase locking protocol, which guarantees conflict serializability. It does a simple thing. It has two phases: a growing phase, where a transaction may obtain locks and may not release any lock, and a shrinking phase where the transaction may release locks and may not obtain any locks. So, you are just separating out the the grant or the access of locks, holding of locks, and the releasing of locks into two different phases. You do not mix them up, and that is the two phases of the locking protocol. And this ensures, so we will not do the proof, but you can look it up in the book, or you can see it through examples, that it can be shown that transactions can be serialized in the order of the points where they do the locking. So, these are known as lock points, and that is where the transaction actually acquired its final lock. So, there can be conflict serializable schedules that cannot be obtained if two-phase locking is used. So, what this is saying is, if you use two-phase locking, you are guaranteed to have conflict serializable schedule, but there are conflict serializable schedules for which you may not be able to honor the two-phase locking protocol. So, two-phase locking protocol is kind of a sufficiency condition. So, you could also refine the two-phase locking with what is known as lock conversion. That is, you can acquire in the growing phase or the first phase, you can acquire a exclusive lock, a shared lock, or you can convert a shared lock that you already have into an exclusive lock, which is called the lock upgrade process. Similarly, in the shrinking phase, you can release a shared lock, release an exclusive lock, or you are holding an exclusive lock, you can make it a shared lock. So, you can downgrade. So, you can understand that upgrade and downgrade are strategies to only use that much of restriction that you need to impose on others, and to allow others to access the data to the best possible way. This protocol again assures serializability, and it certainly depends on the programmer as to how the programmer inserts the various locking instructions. Now, you will have to, when you want to do read or write, you may acquire locks automatically. The database systems will allow that. So, this is a very simple algorithm. So, if you want to read a data, if you have a lock already on that, whether it is shared or exclusive, you can simply read it. If you do not have that, then if you may have to wait until no other transaction has an exclusive lock on that, because you know that read or shared lock is not compatible with the exclusive lock. So, you may have to wait till all other in no other transaction, the transaction that was having exclusive lock possibly has released it, and then take a grant of the shared lock on this item and then read it. It is a very simple algorithm to automatically acquire locks. Write is little bit more complex, because to be able to write, either you already have an exclusive lock on D, then you can write, or you may have to wait till no other transaction has any lock, because exclusive lock is not compatible with shared lock or with other exclusive lock. So, as long as some transaction has a lock on D, you cannot proceed, but once you come to a state that you already, if no other transaction has a lock, then you see whether you yourself have a shared lock on D. If you have a shared lock, then you upgrade it to an exclusive lock. If you do not have a shared lock, then you take a grant of the exclusive lock, and then you can go and write. So, it is, if you follow the two phases, these algorithms become very simple, and when you commit or abort the transaction, then naturally all locks will get released. So, the two phase protocol we have already seen, that does not ensure freedom from deadlock. You may follow two phase locking protocol. Here is an example, but you may still have schedules which will have deadlocks. So, this is one example, you can just convince yourself. There is another problem that can happen in addition to deadlock. There is a possibility of what is known as starvation. Starvation occurs, usually it occurs when the concurrency control manager is not a efficient one. So, what did we see in terms of automatic locks in read and write operation is, you may have to wait because someone else is holding a lock on an item and holding an exclusive lock on the item. Now, it is possible that like the current transaction, there may be a couple of other transactions who are also waiting for a lock on that item, and when the opportunity comes that there is no lock being held by any transaction, one of the waiting transactions must be given the lock. You cannot, if it is an exclusive lock, you cannot give it to more than one transaction, but say 3 transactions were waiting for the exclusive lock and one of them get that, and that transaction can proceed. The other transactions have to roll back because they are not getting the lock. So, now you again come to the point where you wanted the exclusive lock on that item, and at that time somebody is holding it, and there are other transactions who are also requesting for exclusive lock. And when you come back and when finally the exclusive lock is released by all other transactions, then again it is possible that while you are waiting, some other transaction that was waiting gets that exclusive lock and you do not get that. So, you roll back, and this could keep on happening. So, if you have a weak strategy in terms of concurrency control, you will see that you have had infinite possibilities, infinite occurrences where you could have got that exclusive lock, but you are not being able to get that, and therefore, you starve on the data, and this is known as a starvation problem, which will also have to be checked while we do the concurrency control policies. There is the potential for deadlock exists in most locking protocols, as we have seen, and when a deadlock occurs, there is a possibility of cascading rollback, because when a deadlock happens, then naturally you will have to roll back. So, you may have to do a cascading rollback, as this example is showing, and it is possible for a two phase locking protocol. We have an example is shown here, where all the transactions are following cascading rollback, as following two phase locking protocol, but if T5 fails after the read step of T7, after the read step of T7, if T5 fails, then it leads to a cascading rollback. T5 has to be rolled back, so T6 will have to be rolled back, so T7 will have to be rolled back, and so on. Interestingly, there are several other protocols, and particularly two more two phase locking protocol. One is called strict two phase locking, which avoids cascading rollback, where a transaction must hold all exclusive locks till it finally commits and aborts. Naturally, you can figure out that you are making the time for the transaction to hold lock longer. So, naturally the level of concurrency will go down, that is all possible serializable schedules will be smaller, but this guarantees that you will not have a cascading rollback. And there is an even stricter rigorous two phase locking, where all locks are held till commit or abort. In the strict one, only exclusive locks are held till commit or abort, that is till the end of the transaction, but in rigorous two phase locking, all locks are held till the commit or abort. In this protocol, transaction can be serialized in the order in which they do the commit, and in that way this is a serializable protocol, which also avoids the cascading rollback. Now, finally, before we close this module, a quick word in terms of how do you implement locking. It is the lock, there is a lock manager which implements the locking. The lock manager itself runs on a different process to which every transaction send lock and unlock request, and the lock manager maintains a data structure to maintain who are the transactions who are holding different locks on different items, and based on that the grant messages are queued on that data structure, and release messages actually release the locks, and otherwise the transaction has to wait. The lock manager maintains this as a lock table, and this is typically a in memory hash table, because it needs to naturally be very fast and is in the name of the data item being locked. So, let us just show you, and so these are the different this is an instance of a lock table, and the nodes are different data items. So, I7, I9, 12, I4, I44, I23 are different data items. There is a hash table. So, you can see that on I7 and I23 there is a collision and there is a coalesce chain happening on that. And then for every item you maintain a list of locks that are granted to different transactions and the list of requests that are waiting. The dark blue here shows the grant, and the light blue shows the waiting status here. So, it takes naturally says what type of lock is granted and requested, and based on this, therefore, when you get a request, you put it in the, you come and put it, you hash it to that data item, put that request on the queue, and based on the current status you can decide whether it can be granted or it has to wait. So, it is added, new requests are added at the end of the queue, it is first in first out, and whenever a release happens, then naturally a granted node is removed and a waiting node might get a chance to lock that item. If the transaction aborts, all waiting or granted requests of the transactions certainly will get deleted. Okay. So, this is a simple way to manage the locks. So, in this module on concurrency control, we have understood the basic locking mechanism and protocols. We have specifically looked at the lock compatibility matrix and the strategies of granting and releasing locks, and we have seen the consequent danger of having deadlock and in some cases starvation, which we have agreed to live with. So, if deadlock happens, we will have to roll back one or more transactions and then restart again, and but we cannot take the risk of not having serializable transactions, because that might lead to inconsistent state of the database, which is not acceptable.